We're gonna start to calculate the reinforcement for this one-way slab. This slab has 11 by 5. The major side is 11 meters and the shorter side 5 meters. We start by estimating the total depth. Total depth I like to calculate by the shortest span divided by 20. Usually gives me a good estimation. And here, so 5 meters divided by 20, meaning 25, 0.25 meters. The effective depth usually it's between the one-way slab, simply reinforced 3 cm distance. The distance usually I calculate by this equation. It is the total depth subtracted by the clean cover subtracted by half of the diameter. Here it's gonna give us, and this is usually 3 cm that we subtract from the total depth. So here give me 22 centimeters. For this concrete we're gonna use the resistance of 30, so it's C30, 37. For steel we're gonna use A500 or S500. It can be designated in some manufacturers of iron rods by other designations depending which country is manufactured. It can be F500, but what really matters is that is 500 is resistance, the steel. So then we'll need this value. We know the FCD, that we use a safety factor of 1.5. So we divided the 30 of the concrete by 1.5. Give us the FCD. For the iron rods we divided 500 by 1.15. that is the safety factor of this. This gives us the FYD of the steel. We're gonna consider on the slab something more realistic to what usually we calculate in the buildings. So we have here we have to determine self-weight, that will be the total depth 0.25 meters multiplied by the density of the concrete 25, give us this value. For floor finish we're gonna consider 1.5 and we're gonna consider a live load of 5 that is about 590 kilos. If we think this is people, so it means in a square meter we have 509 kilos per square meter. If we consider it people. In the old British code, the variable load and the live load were the same. So but here we make the difference between, and it's basically the same. Well, we know this is a one-way slab when we look for this, and we see that is supported in two opposite sides here in the minor side. so it's immediately looking to where it's a one-way slab. When we don't know, we divided the major span by the minor span. If it gives us bigger or equal to 2, it's a one-way slab. In this case, give us 2.2, so it's a one-way slab. To calculate this reinforcement, we have to check the ultimate limit state, that in the Eurocode it's calculated by this equation, that we're gonna factor these loads 1.35 multiplied by the permanent loads, that is in this case is the 6.25 plus the 1.5 plus the variable load multiplied by 1.5, and we can consider the live load 1.5, the factor. So in this will give us 1796. And for this ultimate limit state, what we want is deflection. So we need the moment. The moment in a simple supported beam, it's calculated by this weight factor multiplied by the length, that is the minor span, elevated by 2 divided by 8. So, and this will give us the 56.13. And for shear, from resistance calculation, we know it will be the weight factor multiplied by the length divided by 2. This, in this case, 44.9 kilonewtons. And we calculate it for the shorter span because it gives us less iron to span. We calculate the reduced bending moment, that in the British code, Eurocode, it can be called it's a non-dimensional moment parameter. That we can call it K. I call it mil. It can be K. So you're gonna see tables there are call it K instead of the mil that I use. So this is equal. This reduced bending moment is a non-dimensional parameter. So it's the factor moment that we calculated there divided by B, multiplied by D, elevated by 2, multiplied by FCD. And this we already calculated there. So is this moment divided by BD, that is 1 meter. We are considering a section of 1 meter on this calculation. We are consider 1 meter in the section for this calculation. Multiplied by D, the effective depth. The effective depth 0.22. This we multiply by, here is divided by 1000 because we pass all the units to the same, and so it gives us 0.058. With this we're gonna check this K, or this reduced bending moment in tables, and there is a limit already calculated for this, and the limit for this concrete and steel is C30, 37 to A500. Still, if we're gonna go to the tables and check the mil is still 500, steel concrete less than 15 give us 0.371. Okay, so the K limit is 0.371 mil limit, and when we check this condition, what we calculated was 0.057, and this is less or equal to 0.371 that is already pre-calculated in tables. We can say so that is a simply reinforced. K1 and K2 is values already on Eurocode. They are fixed values for this situation. With this K, with this reduced bending moment, we can get the percentage of steel for the main reinforcement that we are after. And this is using this equation where we have the K here. It is the mil that I'm using. So when we multiply everything and divide this, we get 0.059% for the main reinforcement. We go to the equation of the main reinforcement, where we have the percentage of main reinforcement multiplied by B, that is 1 meter, multiplied by the effective depth, that is D, that is 22, multiplied by FCD, that is 20, divided by FYD, that is the FYD is the 500 divided by the safety factor 1.15. This will give us 6.05 square centimeters per meter for main reinforcement of steel. So when for spacing of this main reinforcement, I like to limit it to 25 centimeters. And in some codes in Europe you have this spacing. You can determine it by 1.5 multiplied by the height, and since I limited this to 25, so you use the minimum value between 1.5 multiplied by the height or 25. In this case it gives us 0.25 meters. What if we try to use it here, 25, to give us we have to use like bars of 16, and the difference is almost 2 square centimeters. So this is why I was using 12 here, and I prefer to use spaces of it's not enough, so I have to go to space of 15 cm, and here it's 6. Spaced by 15 give me 7.5, but if I lower here it's not enough, the steel. Oh, as we can see, it's not enough here, the steel, so this is why I'm using 12. And for the main reinforcement here it's okay, but we need to check the minimum reinforcement, if it's check the minimum reinforcement. So for the minimum reinforcement is this the equation, 0.26 multiplied by FCTM multiplied by B on traction, tension, multiplied by the effective depth divided by FYK. On this concrete FCTM it's 2.9. Is checked on the tables according to the concrete. C3037 FCTM 2.9, FCTM 2.9. Okay, so when we multiply this equation, we put it everything in centimeters, of course, we'll get 3.31. So this minimum steel is verifying the main reinforcement. Yes, because it's 6, it's bigger, it's okay. So now for the distribution. The distribution reinforcement will be 20% of the main. So it's 0.20 multiplied by 6.05, what gives us this small quantity. But since I like to follow a rule that I maintain always the minimum reinforcement, and we calculated there that it was 3.317, and for this using steel of iron rods of 8 millimeters spaced by 15, that's 335, what is a little bigger than this, so this is okay. So for the distribution we're gonna use the same. I like to adopt the diameter of 8 spaced by 15 is 3.35. that check my minimum reinforcement. Then so we have this main reinforcement and distribution reinforcement on the bottom of the slab. That is here, so you're gonna see it here. This is in the 5 meter span, 12 of, and for distribution diameter of 8 spaced by 15. Now we calculate for the in the corners, in the supports, due to the rigidity you can have there some cracks, so we need to calculate there it can happen here, cracks close to the beams. For that we calculate this reinforcement on the top and some distribution reinforcement on the top for the supports, one side and to the other one. Okay, for this calculation we're gonna adopt the maximum value of that will be chosen from the minimum reinforcement, or 25 of the main reinforcement, 25% of the main reinforcement. What gives us 3.31? We can check 0.25 by the main reinforcement. Here it was given 151, but the minimum is 3. Is 3.31 the minimum reinforcement, so we're gonna adopt, and we already know the diameter of 8 spaced by 15, 3.35 to check. And then for distribution of the support it's 20%. 20% of what we calculated for the reinforcement on support, what gives us very small quantity, but I like to adopt the minimum value So I maintain diameter of 8 spaced by 15, that is 3.35, and we get this result. Here the main reinforcement, the distribution bars, the reinforcement on support and the distribution of the support. You can see here. So the main reinforcement along the minor span, the distribution, diameter of 8 spaced by 15, that is along the major span. We can see here along the major span that is this one. On the bottom, diameter of 8 spaced by 15. In the bigger span, it's along them. And here this reinforcement was placed to protect from cracks due to the rigidity here, because can have some here is positive moment and here can have a negative moments on the corners. So we place it on this distance L divided by 4, this reinforcement. We know that some softwares will there are some softwares in the market that what they gonna do, they're gonna continue this reinforcement here on support and connect it to the other side and bring the distribution bars here. That will be checking the minimum because of the fact that in the program it will be calculating already combinations. That, for example, in this calculation we don't have here traction on the top of this section, but with combinations it can happen, or by wind that can force. So having a minimal reinforcement here on the top too, it will be advised on that conditions can be a building with strong wind or some other axial force making slab having traction here. So this is why the softwares, some softwares will give this premium calculation with the steel here on the top too. For economic purpose, if you can guarantee there will be no traction here, this is the ideal reinforcement, as we can see here in this calculation in a software that I will not say the name. What they did is exactly that, so our diameter on the bottom of 12, and what is done in a detailed way is that it's spaced here by 30 and we calculate it by 15, so it is exactly the same. What happens is that one iron rod is placed and after 15 centimeters is placed, so another iron rod, because here in the support we only need 50% of the reinforcement. Yes, this is why this one goes till the support one side to the other one and doesn't go more, because we can put one time one this length, another one full length, then we get to the 50% only of steel that we need here on the bottom. And on the top here, what happened with this connection one side to the other is what I told about the combinations. There will be one combination one time always. We calculate for several combinations, there will be traction here. So placing the minimum reinforcement, it's good. This is why we have a diameter of 15 here, and along we have the same thing. for the distribution bar, diameter of 8 specify 15, and on the top the same. The only difference was this, the combination that can have wind or other forces involved in a total calculation in a building. Okay. So this is what we get for economic purpose. Now we need to check. We check the flexure for the bending moment. Now we're gonna check for shear. And for shear in the Eurocode we have this equation, the VSD, that is the shear that we calculated before here on top. It was 44.9 in the ultimate limit state, 44.9, and we need to calculate this CRD. The CRD is equal to 0.18 divided by a safety factor of 1.5, it gives us 0.12. The K is calculated on this equation with the effective depth, the D on millimeters, and it has to be less or equal to 2, and in this case it is. So we use this K for here, this multiplied by 100 rho of the longitudinal, or the rho. In this case we don't have axial force, or we don't have the axial force, so it will be 0 here, and this other side 0 too. The FCK is the 30 elevated by 1/3. So this equation is saying that which value is bigger, this one or this one, is the one that we're gonna compare with the shear that we calculated. So for this one we get 112 kilonewtons for the shear resistance, and for this other side in the equation it gives us 115, and what is the maximum between these two is 115. And what we have is this: when we compare, this one is smaller than this one, so it check for shear at ultimate stage. And when this check, it means before that, here the rho that we calculated, it gives us 0.003. So always when it gives us this, you know, it's less than this one, 0.02. If it's less than 0.02, it means the steel gonna yield first than the concrete, so it's fine. It's what we want. So what I was saying is that it checked for safety for shear at ultimate limit state. This equation from Eurocode to 6.2.2. This means that this is for members not requiring shear reinforcement. So that's why we don't need to put stirrups there. So everything is fine. And we can look here to detailing. Main reinforcement, diameter of 12, specified by 15. Distribution of the main reinforcement, diameter of 8, specified by 15. For the super, diameter of 8, specified by 15. For the distribution of the super, diameter of 8, specified by 15. We have very harmonious reinforcement here.